What I find most valuable about being here in person is the opportunity to interact with other people that are the best in my industry about the issues that are important to me and at my workplace.
All right, I'm Andrew. I work for the Ladybird Browser Initiative on the Ladybird Browser. And today I'm going to talk about improving an HTML parser with pattern matching. I lied. I'm going to talk about an HTML tokenizer, but it's part of the parser. But the most important thing to recognize about the HTML tokenizer is that if you actually go to the spec, which I linked at the bottom of the slide, it's very well spec'd. Like, this is the page on parsing HTML in the HTML spec, and it lists out all 80 states of the parser that you have to implement, and every one of those states has everything you're supposed to do. It also explains how the tokenizer is supposed to interact with the parser, because they talk to each other, because of course you can inject things with scripts and whatever else. But let's talk about Ladybird's HTML tokenizer. So in Ladybird, our goal is to match the spec as closely as possible, because we're implementing the web specs from scratch. So we want to make sure that we're standards compliant. And this is the very first state, the data state. It says, oh, we're supposed to consume the next input character. We're supposed to, check what it is. Is it, this character? Is it that character? If it is, then either emit a parse error or, set some state and go to a different state, or emit an end of file or whatever else. And what I'm about to show you is the state of the current HTML parser in Ladybird, which is actually the second parser we wrote, because the first one was just like, oh, maybe we could parse HTML if we tried, and we just wrote some code. But this is the one that actually we looked at the spec and wrote it to the spec. So here we go. So we're trying to match it as exactly as possible. So wait, why are those highlighted yellow? How did we implement this exactly? Oh yeah, we did it with a lot of macros. So if we look back again, each of those things is just another macro. There's 15 of them at the top of the file. And here's the begin state and the end state. And why is there a label above my case for my giant switch statement? How did we implement this exactly? Oh yeah. When we go to another state, we go to another state. So this is how we implemented all those nice, pretty statements in the spec that said, oh yeah, you should reconsume this input character in that state. So we just go to that state. Or if we're supposed to reconsume in the return state, we go back to the top of the function and check our queue of tokens and maybe return one of those. And then we check the state, which was the return state. And well, it follows the spec almost exactly, and you can read it, and it reads like the spec, so what's the problem? Yeah, okay. So can we do better than this? I think we can. So, over this past year, we've been looking at successor languages on the project to see if there's something we can do to, improve the memory safety of our browser, because browsers have a massive attack surface, and we should probably do something about memory safety. So we looked at a couple options. One of them was Rust, obviously. We looked at Swift as well, because Swift 6 released literally yesterday, and it's got a lot of C++ interop features. We looked at something from Phil Pislow called PhilC. It's very interesting. He wants to compile the world with a garbage collector and guarantee memory safety that way. It's an interesting approach. But the whole point is anywhere we've got untrusted input, we want to look and see, can a successor language help with this? So let's re-implement this in Swift. And it's got pattern matching, it's got choice types, so how does that work? Well, instead of all these macros, I've got this state machine at the top that, instead of go-tos and actually returning from this thing, I just have a top-level state machine that says, are we emitting a token? Are we switching to a new state? Are we reconsuming? Whatever else. Okay. So all of those macros just become functions, and we can return this enum, or this choice type, and it seems to help drive that top-level state machine a little bit better. And what does our data state look like? Well, this just looks absolutely pleasant, if you ask me. There's no macros, and we're just using pattern matching. And we say, look at the current input character. Is it one of these? Is there no input character? Because we're actually matching on an optional here. emit EOF, and looks quite pleasant to me. So my question is, when are we going to get this in C++ again? Wasn't there some paper? I don't know. But that's all I've got for you. We transformed this ugly macro-ridden mess into some nice, beautiful pattern matching.